sampling theorem, saying x of t is equal to x of t and delta t of t, and using the frequency convolution property. So what the frequency convolution properties would say that Fourier transform of x of t, let's call it x hat of f, is, and let's Fourier transform of x of t is x of f, and then Fourier transform of delta t of t is equal to delta of f. Put t here as well. What does the frequency convolution property say? If I have a multiplication in the time domain, then the spectrum of the signal is the convolution of the frequency domain. So in other words, it would have to be x of f convolved with delta t of f. Okay, so that's what we know. So now the question is, how do I determine delta t of f? What's the Fourier transform of this signal delta t of t? And we say, well, delta t of t is going to be sum when n goes from minus infinity to plus infinity, delta of t minus n ds. So Fourier transform of delta t of t is going to be equal sum when n goes from minus infinity to plus infinity. What's the Fourier transform of this guy? It's 1 e to the minus j n ds times 2 pi f, right? 2 pi f n d. So that's the Fourier transform of delta t of t. So now, what I know is that x f of f is equal to x of f convolved with this sum, and goes from minus infinity to plus infinity e to the minus j 2 pi n f 2 pi f n ds. Right? So can we get out of this thing? If I have, let's just refresh memory, f of x of f convolved with y of f is given to what? The integral when nu goes from minus infinity to plus infinity, x of nu, y of f minus nu d nu, right? That's how I would calculate the, is there a complex conjugate here? Do you remember? Let's do without it. So I guess here, this becomes now integral when f goes from minus, let's say nu goes from minus infinity plus infinity, x of nu times sum when n goes from minus infinity plus infinity e to the minus j 2 pi f minus nu and ds, and then d nu. Right? So that's what the spectrum of x of f looks like, well, x capital F. So let's just expand this. So this is now sum when n goes from minus infinity to plus infinity, integral when nu goes from minus infinity plus infinity, and then this comes this e to the j 2 pi f nts goes outside, so what's left is x of nu times e to the j 2 pi nu ATS, the nu in e to the minus j 2 pi f dx. Okay? And why is this sampling here? So let's see. What is it that we're trying to prove in the first place? There was that formula. The first one of the two. Okay, yeah. Okay, so what is this thing here? This is inverse Fourier transform. Do you see that? And when t is equal to nts. Okay? So this is equal to sum when n goes from minus infinity to plus infinity, x of nts, and then e to the minus j 2 pi f n dx, right? So that's a spectrum of the sample signal. Now, if I take the inverse Fourier transform of both sides, on the left-hand side, I have x of t. And then, if I take the inverse Fourier transform of this is just a constant. So this becomes sum when n goes from minus infinity to plus infinity, x of nts. And then you have integral when f goes from minus infinity to plus infinity. So this is 1 times e to the minus j 2 pi f n ds, and times e to the j 2 pi f n f t d. Right? And now if you look at what this is sum, and n goes from minus infinity to plus infinity, x of nts. This needs to somehow become sync. So let's see how does this become sync. E to the, you can say it here, j 2 pi f p minus n df. And this is essentially sum when n goes from minus infinity plus infinity, x of nts times delta of t minus nts. So that's our sampling here, right? Saying that if I started by looking at what this is, and I kind of looped around. I don't know if this is proof of what the problem was asking, right? Is it? It says, derive the sampling theorem by considering the fact that the sample signal x hat of t in using the frequency convolution problem. 743. So I need to look at what he has in those equations. I mean, everything is correct here. It's just, I just don't know if that's what was required. So 743, okay, 743 is this one here. This is 743. Saying that x of t, x1 of t, x2 of t have a Fourier transform as x1 of f convol with x2 of f. That's the frequency convolution. But what is the other one? Okay. And what is it that we really need to prove? We need to prove that x of t is equal to sum n goes from minus infinity to plus infinity x of nts times sinc of t minus n. That's the statement of the. Maybe there's some. So how do we get that from all the stuff that I wrote here? We have that, so x of t this is looking fine on me, but so I would have to think. I don't know at this point. I mean, it's a spin of on the equation that he is trying to put here. So all of this is true. Right? That if you take the x hat of t, this is x hat of f, right? And you can see that it's this. And then the question is, okay, if I'm hat of t. So how do I? That is this. So let me just do one more. Can I do that? I don't see right now how to spin this equation, but this is yet another. This is the formula that we showed last time, direct way. Now what I'm showing it is actually by using the convolution property of the convolution property in frequency domain. But and then if you invert this formula, you get the sampling, right? But it doesn't prove. I haven't proven this. I need to think about how you can actually demonstrate that. Let me think about it and then we can look it up next time. Any other questions? Okay, go ahead.
8.12. Part C.
8.12 part C. Okay, so let's talk about this thing in general. This is a very important property that was assigned for you as a homework. I don't know if you guys. I hope you kind of went through it. And here's the question. This is before we go to that problem. Here's what you need to know. Let x of t and x of f be Fourier transform pairs, and y of t and y of f be Fourier transform pairs. Right? So I have two functions, x of t and y of t, and these are their Fourier transform pairs. The first property is that if bandwidth of, let me actually do it like this, and let bx be bandwidth of x of f or x of t, and by bandwidth of y of f, right? Both of these are band limited, having these bandwidths, right? So if I define a signal, let me do a couple examples. Z of t, which is equal to x of t to the power of n. What is the bandwidth of z? What's the bandwidth of this signal? Now, the way how you can see it, let's look at the special case determined, let's say here, bandwidth of z. Let's take a look at special case n equal 2, right? So, if for n equal to z of t is equal to x squared of t, right? So I'm looking at what is the bandwidth of x squared of t, right? If the bandwidth of x of t is equal to bx. Now the way how you understand this is x of t times x of t, right? So it's product of x of t with itself. If I take the Fourier transform of both sides, you get that z of f is equal to x of f convolved with x of f itself. If the bandwidth of x of f is bx, what's the bandwidth of this whole thing? 2bx, right? Because the convolution does smearing. If the length of a signal is, let's say, f in a frequency b, x in a frequency domain, and the convolution on the width of the signal again is bx, then the width of the convolution between these two signals is 2bx. So in this case, bz is equal to bx. How about in the general case for any n? So bz is going to be what? N times bx. Okay? That's one way of seeing this. And this is by looking at the multiplication of time domain as a convolution in the frequency domain. Maybe more intuitive way to see this is this. Now I'm going to do a little bit of draw. Let's say this is your x of f, right? The Fourier transform of the signal x of t. Now, if you put your Fourier series glasses, you have a whole bunch of sinusoidals that are existing here, right? All of these guys. And if you look at one-sided, let me actually look at this as a one-sided spectrum so that it's more clear physically what is happening. So this is f, and this is now the spectrum of x of f, but these are all positive, just the magnitude of the sinusoidals that participate in building this x of f. If I draw it like this, because the spectrum is discrete, you know, in my drawing, the x of t would be periodic, but if I make all of these sinusoidals infinitely close, then I end up in limit obtaining non-periodic signal. Now, think of this as a sum of sinusoidals. What happens when I sum all of these sinusoidals, when I take the square of it? Let's say something like this. X of t is going to be approximately sum over n, some magnitude, let me call it Cn, cosine 2 pi n f0 or n times delta f t plus some phi, right? N. What is it that I'm saying? I can build this sinusoidal as a whole bunch of sinusoidals that are separated delta f in a time domain, right? In a frequency domain. And then this, as this delta f becomes smaller and smaller, me building this x of t is better and better, right? I actually ultimately, as delta f becomes infinitesimally small, I actually get my inverse Fourier transform. Now, if you take x squared of t, you actually end up squaring all of this. Cn cosine 2 pi n delta f t plus phi n, and then the whole thing squared. And you know when we square this, what do we get? We get all components squared plus 2 times every cross product, right? And then every product gives us the sum and a difference, right? So I can write this as a sum, let's say n, sum over m, Cn, Cm, cosine 2 pi n delta ft plus phi n, and then times cosine 2 pi n delta ft plus phi n, right? I have, you know, all of these terms that I need to deal with. Now, if you look at each one of these individual terms, you say cosine n times cosine n cosine m delta f. So you're going to get the sum, and you're going to get the difference. The difference are going to be generating components that are towards the origin, right? Because the difference can be as small as 1 delta f, you know, and as large as single delta f. But what will push the spectrum of the signal is the sums, right? Sums are going to extend beyond, right? Because look at, for example, the multiplication of these two. Their sum is going to be here, right? You follow so far? So how far the sum can extend? What's the largest one? Well, it's the last one in this summation when this is capital N, for example. So if I look at this last one times itself, it's going to give me the component at twice its frequency. Which, if the last one has a bandwidth of b, then the twice is going to be 2b. Do you follow? So physically, that's what's happening. You have this mixture, all of these components, and they're going to generate all of their sums and differences. The one that is furthest to the right is going to be sum attributed to the highest frequency component. So x squared is going to have the bandwidth of 2 times b, 2 times bx. I mean, mathematically you can prove it like this, but this is not the most intuitive way how you can understand it. The most intuitive way is think of a signal as a bunch of sinusoidals. When you square it, you're generating all the products between each other. The one that is furthest to the right is going to be the one associated with the highest frequency in the spectrum of the signal, and it's going to be twice the frequency, right? Because it's squared, right? And squared gives you DC component and twice the frequency. So that's going to push you all the way to twice the band. So when you square the signal, the bandwidth of it is 2 times larger than the signal itself. When you cube it, guess what? It's 3 times larger, right? And so on. When you raise it to the power n, then it's n times large. So that's one result. The second result is if z of t is equal to x of t times y of t, then bandwidth of z is going to be what? It's going to be bx plus by, right? Again, think of this as because you're going to have z of f be convolution of x of f convolved with y of f, right? And if you think of these as two signals in a frequency domain, then the length of their convolution is equal to the sum of the lengths of these two signals. So this is now you can extend that to multiple, more than 2, right? If you have 3, then it's sum of their bandwidths and so on. Okay, so now let's apply these two results to the problems that are in this 8.1. 8.1 point C, I said. Is that the one?
Yeah.
8.1-2 point C. It says, determine the Nyquist sampling rate and the sampling interval for the signals. So here x is equal to sinc of 100 pi t plus 3 sinc squared of 60 pi t. Okay, before I actually realized, I forgot to do one more thing here. Let me do third result. If z of t is equal to x of t plus y of t, what is the bandwidth of z? We have two signals. Remember, the superposition holds. So the spectrum, if you look at here, z of f is going to be x of f plus y of f. So if this is your x of f, let's say like this, and this is your y of f, let's say like this, how does your z of f spectrum look like? It's something like this, right? So if this is a bx, and this is by, what is bz? Bz is going to be equal to the maximum of bx and by, right? If you sum the two signals, then the bandwidth of the sum is the maximum of the bandwidth of the two. Remember how we see signals. We have the bunch of sinusoids. So when you add them, you cannot create the new sinusoids. Here, the squared is the nonlinear operation, right? Therefore, you're getting new frequencies. But addition is a linear operation, and it cannot create new frequencies. So whatever was the content of the first signal and the second signal remains as the content of the third signal, right? So therefore, the bandwidth is not going to expand. It's going to be whatever is the larger of the two of these bandwidths. So that's the considerations prior to working out this problem. So I have this signal x now consisting of two signals. This is x1 of t, and this is x2 of t. What is the Fourier transform of x1 of t? It's the Fourier transform of the sinc. Now, I know this is a square pulse, but let's. What page are the Fourier transforms? Do you remember?
Chapter 7.
I know chapter 7, but where is the page with the table? 7.2. The table of Fourier transform.
I think it's
There it is.
1 over square root of 2.
Okay. So if I have a sinc pi t, if you look at entry number 18, entry number 18 tells me that here's the result that I know, that W over pi sinc WT is going to have a Fourier transform rectangular of 2 pi f over 2 W. Right? So that's the Fourier transform P. So if I look at this guy here, then x1 of f is going to be, I guess, pi over 100 pi times the rectangular of, I guess, omega over 2w, which is 2 times 100 pi. That's the Fourier transform of the first one. Did I do it right? If you look at that this W here is 100 pi. So I'm missing W over pi here, so I put it on the right-hand side. W over pi. Where did I? Oh, so I have to put pi over here and divide by W, but W is 100 pi, right? And then rectangular, or this is omega divided by 2 times W. This is W, this whole thing. Right? So that's the x1 of f. x2 of f is going to be 3 times pi over 60 pi rectangular omega over 2 times 60 pi. Okay? So that's the Fourier transform of the second. So now I draw these two guys. So x1 of f is a rectangular pulse. Let's say this is omega. So this is x1 of f. And x1 of f occupies, it's centered, of course, at the origin, and it occupies up to 100 pi. Right? 100 pi. So this is the Fourier transform of the x1 of f. x1 of f. Fourier transform of x2 of f. It goes from minus 60 to 60. Right? So it looks like this. This here magnitude is 1 over 100, and this magnitude here is 3 over 60, so 1 over 20. Right? So that's the bandwidth of x2 of f. So the bandwidth of the signal x is going to be maximum of these two bandwidths. There's a pi here, right? Pi. It's going to be 100 pi divided by 2 pi, which is going to be 50. So that's the bandwidth, right? In frequency, f, in hertz, right? Because the bandwidth in radians is going to be the larger of these 200 pi, which is 100 pi radians, which is 50 hertz. Go ahead.
Isn't there a square of x2?
Yeah, sin squared.
Oh, okay.
So it's going to be 120 pi?
Oh, okay. So I messed up. Thank you for correcting. So sin squared. Let me just do it like this and have to sin squared, right? So that in this case, this is the bandwidth, and the sampling frequency would have to be 2 times px, which is 100 hertz. Now, if I define a second signal, this is x1, or not x1, xa, xb, as sync of 100 pi t plus 3 sync squared of 60 pi t. Then, as far as x1 is concerned, it stays the same, right? So I have the bandwidth like this, 100 pi. And when I draw the second one, then it actually extends to 120 because it's sin squared. So in this case, the bandwidth of xb is going to be 120 pi divided by 2 pi, which ends up being 60 hertz. And then your sampling frequency would have to be 120. Okay? So that's but these are important results, right? This appears all the time when you're in communications, right? In communication we have, let's say, AM, FM modulation and those things, and we always end up having square terms or multiple power terms. And it's important to understand in a bandwidth where these terms would extend. How far would they extend? Okay. So that's the, any other? The other ones should be relatively easy. If you look at, let's just answer them if we can by heart, right? by what we know by now. So A part is sinc squared of 100 pi t. So the bandwidth of sinc of 100 pi t is 100 pi in radians. So sinc squared would have 200 pi divided by 2 pi is 100 hertz. So the sampling frequency here needs to be 200 hertz, right? The bandwidth is 100 hertz. And then part B was 0.01 sinc squared of 100 pi t. How about this one? Do these have a different bandwidth? No, because they're essentially the same functions, just scaled in magnitude. So here the bandwidth is the same, 100 hertz, and your sampling is 200 hertz. And the last one is interesting. So part D, you have sinc of 50 pi t times sinc of 100 pi t. So the bandwidth of this one was 50 pi divided by 2 pi. So it's 25. What am I missing something? Or so it is 50 pi radians. So divided by
2 pi.
Yeah, by 2 pi is 25. So this one is 25 hertz, D1. And this guy here, D2,
50 hertz.
is 50 hertz. So how large is the bandwidth of the product?
75?
75. 75 hertz. Because you're going to get product in sum of all the components, and then the largest one is going to be the last component here, which sits at 25 hertz. The last component here, which sits at 50 hertz, and their sum is going to sit at 75 hertz. The rest of them are going to occupy the spectra in between. Okay? Any questions? Go ahead.
818.
818. It says the highest frequency in the spectrum of X of omega, given in, this is the one given in the figure C818, okay. So it's 30, okay. So that's, this is, I guess, F axis. And you have a signal that looks like this. So this is minus 30, minus 20, 20, 30. And this is, I guess they make a typo here. It should be X of F, right? They put X of omega, but it should be X of F. Right? Because on the X-axis is F. You see that in the book they put X of omega. So it's a bandpass signal, it's 30 hertz. Hence the minimum sampling frequency needed for this one is 60 hertz. Show that the spectrum of the signal, sampled at the rate 60 hertz. Can you reconstruct X of t from these samples? How? Okay. So is that the part or part A or part B? Part A, okay. So now if I sample this signal at 60 hertz, what does the sampling do? How do we understand the sampling in a frequency domain? Remember, that was one of the most important derivations last time. Sampling in the time domain is equivalent to the frequency periodic extension in the frequency domain. So let's do that. you know, here I'm gonna kind of draw a larger x-axis. So here's 0, here's your 30, where sampling at 60, so this is 60, so this is 90, this is 120. There is a first version, remember the sample signal, x hat of f, is going to be equal sum when n goes from minus infinity to plus infinity, x of f minus n fs. That's the spectrum of the sample signal. So I have the first, when n is equal to 0, I get this piece, and then equivalent piece on the other side. Let me actually draw it. Minus 20, minus 30. So this is the graph. Then you have to take this whole signal and position that at 60, right? So let's do that. So you're gonna have 60 now. Treat that as a 0. Now this is gonna be 60. This is 20. So this is gonna be 60 plus 20, which is what? 80. So that's this part. So you're gonna have a triangle here. And then this is gonna be 60 minus 20, which is 40. So there's gonna be triangle here. Okay. So let me this is the right hand guy, and this is the right hand guy, and this is the left hand guy. This guy. So this whole spectrum shifted over here. And now I need to shift it again. So this is 60, so I need a bigger board, right? So this is F. So if I want to replicate this one more time, so this is again, so 60, 120 here. And then you get 60, so you get again this one, and then this one, and so on. So this is going to be 100, this is going to be 120, 140, 150, and so on. So that's the sample version of this signal. Okay? Go ahead.
So we just talked about how if you multiply two signals with bandwidth add. Can you elaborate a little bit how we go from two finite bandwidth to an infinite bandwidth then in the frequency domain of the sample?
Well, okay, that's the whole point. You have one of them, sampling is x hat of t is equal to x of t times delta of t, right? Let's look at the bandwidth of these signals. X of t, I know is x of f is identically equal to 0 whenever f is greater than b, right? So this is a band limited signal. But how about this delta t of t? We said, we looked at the last time, delta t of t was essentially equal, I can write it like this, 1 over t plus 2 over t times sum, and then goes from 1 to infinity, cosine 2 pi and fs t. So that was my delta t of t. So what is the bandwidth of this guy? Infinite, right? So you have essentially, and if you look at this, if you do this as if you take the Fourier transform of this, then you end up with a whole bunch of impulses, right? In a frequency domain. And then when you convolve these impulses with the original signal, you get the sampling field, right? That was the original question. So that's how you would go about this. The first problem, you would take the Fourier transform of this, you're going to get a whole bunch of impulses, and when you convolve these impulses, you actually end up with this, with the extension frequency. So now this is the spectrum of the signal. Now the question is, can you reconstruct x of t from these? Show the spectrum is 60. Show the spectrum of the signal. Can you reconstruct x of t from these samples? How? Okay. why I don't necessarily understand the question. You reconstruct it exactly the same way as you would reconstruct it any other sample signal. The catch here is you probably won't be able to reconstruct it, because remember what the reconstruction looks like in the frequency domain. This is the reconstruction in frequency domain, right? I will look at this sample signal, and I have to actually low-pass filter what I need for what I need, right? Low-pass filter in the frequency domain is essentially that sinc weighting function in the time domain. Right? So here, I'm actually sampling at a Nyquist rate. So I have no wiggly room, and I would have to have ideal filter as my reconstruction filter, which is, you know, physically not possible, right? So that's why in this, if I sample the signal at 60 Hertz, I'm just satisfying sampling theorem theoretically, but practically I would have a hard time reconstructing this signal.
But couldn't we do a band pass filter around that one pulse and then frequency shift those two pulses?
These,
Yeah.
just get this.
Did that and then shift each perspective loop back to where it should belong.
You can do a lot of stuff. I don't know if, let's say you filter this, so you end up with this. This is what you end up with, right?
Yeah.
And where do we go from here?
Couldn't we do a frequency shift and then just,
Frequency shift?
yeah, and then just take the upper side band and then the lower side band and then you split it off, upper side band, lower side band.
Yeah, you can,
Do some magic.
those are kind of things that you actually do. I mean, the question is, what happens if you don't sample this at 60, right? Let's sample this at a lower frequency, so I can translate this into something different. Let's say I sample it so that if this is, I would have to draw another. But when the signal is band limited, then you what? Let's do this. Let's shift this over to the baseband, and then sample that with 20 kilohertz, right? Because when I shift this at the baseband, then the bandwidth of my signal is going to be only 5 kilohertz, right? And then I sample with 10 kilohertz and send it wherever I need to send it. And then once I demodulate it, then I shift it back to baseband or to the bandpass, right? So there are other schemes how this can be done. Rarely you do this. Rarely when the signal is like this, you would actually sample it at 60. Let me show you what I'm talking about. Let's say I need to transfer this particular signal to a large distance, right? And I want to save bandwidth in my transmission. So in the step 1, I want to look at the signal x prime of t or x1 of t, which I'm going to take this signal and I'm going to multiply that with a cosine of 25. So it's going to be x of t times cosine 2 pi times 25 t. What will this do? This will take the spectrum of this signal and translate it to the you know how modulation property, you're going to get translation to the sum and the difference, right? So you're going to get the replica of this signal. You're going to get one here. That will be centered at 0, and the other one that will be centered at twice the carrier frequency. So it's going to be centered at 100. Right? So this is 25, no, at 50, sorry. So you're going to get this. You're going to take everything here, and you're essentially translating this to this. So this is the spectrum of x1 of 10. Right. You're going to get this, and you're going to get here minus 50. you're gonna get another one. And these will have a 1/2 of the, so this is what happens when I take this original signal and I multiply this with cosine 25t. Then the next step, it would be to low pass, right? And I get x2 of t to be just this. And then I can sample x2 of t by what is the sampling frequency of x2 of t. What is the sampling frequency of x2 of t?
Should be 10.
Should be 10 or, yeah,
Twice
sorry.
of that.
No. The bandwidth here is 10.
Or 20.
So when you bring it down, it ends up being 5, right? So it's 5. So now you can take this signal and sample that at 10. And then send it on the other end. And on the other end, you will get rid of this right first. So you get x2 of t that looks somewhat like this. Just this. Now this is 5. Now here you can sample this one at 10, and then send this to the other side, and when you reconstruct, you get this one, and now you multiply this again with cosine 25, and this will shift it back to 10. So this way you can save the band. So what you're actually saying, this is stuff that we do, right? In this kind of situation, there is no. What is really the only true thing theoretically here is that derivation that we had. What happens when you sample? And this is you're performing periodic, periodic extension of the signaling frequency domain. That's the number one understanding. And the second understanding is, of course, modulation property of the Fourier transform that allows you to shift the signal back. Okay. Anything else in this problem? Let me see that there's a certain busy student who looks at this signal here and conclude that its bandwidth is really 100 Hertz and decide that the sampling rate 20 Hertz is adequate for sampling x of t. Sketch the spectrum of the signal sampled at a rate of 20 Hertz. Can she reconstruct x of t from these samples? That's a very cool question, so let's see. Maybe she can. So, again, this is our original signal. It starts, this is 0, it goes 20, 30, minus 20, 30. So that's our signal, x over. Now, if I sample this signal at 10, this equation still holds. X hat of f is going to be sum over n, x of f minus n and s. So you have to take this signal and then start delaying it by NFS. So again, I'm going to put this one as dot, and this one is shaded. And okay, so I start with the first one. That's the first guy. This is 25, well, it's 20, 30, minus 30, minus 20. Then I have the one that is delayed by 20. So now this 0 moves to 20, okay? This minus 20 moves to 0. So I have signal that looks like this. This is my minus 10, right? And then this 30 moves to 40, 50, right? So that's my signal, right? This is the second. Then I delay everything by 20 again. So what happens in that case? This this signal now shifts by 20 again. So this minus 10 becomes 10. And then this this is 40, right? This 40 becomes 60. Okay? And the question is, you know, are they going to start overlapping, right? That's the problem, you know? If I shift it again, so then this one, I shift it by another 20, so then this 10 becomes 30, so it wedges in here. And then this 60, no. Yeah, this guy and this guy, right? So by 20, so this and this goes to 60 becomes 70, becomes 80. So you have to do analysis here and see if they're going to actually overlap. And if they never overlap, then you can somehow devise a scheme to reconstruct them, right? But if they start falling on each other, then you're not going to be able to reconstruct them, right?
So can we just say the Nyquist criteria, because that is the basic thing, right?
Well, you have, this is what I'm kind of trying to stress. This is why all of these derivations are important, right? Because you have to understand what does Nyquist criteria mean, right? It is only applicable if the signal is from 0 to W and so on. But this is obviously something that we have some chance of being more economical than Nyquist criteria. Really, this signal here has a bandwidth of 10. It happens to be bandpass signal. So I can do much more economically by doing what I just had, I guess, on the previous board here. Just shift and
Multiplied by cost.
multiply, shift around, and so on. And this is done a lot of time. If you sample bandpass signals, you actually have a way of doing it more efficiently by bringing it to the basement. The Nyquist sampling frequency, this is derived by the fact that if you take a signal that occupies all frequencies from 0 to B, then when you periodically shift so that you don't have aliasing, you have to have Fs greater than 2B. But in the cases where you have some gaps and stuff, you can maybe utilize that to your advantage. Right. Any other questions? How about the other ones? They're okay? One thing about this chapter, well, it's pretty much with the rest of the book too, but this chapter in particular, every problem here is very important. Right? Every problem here is a mini project on its own. It is something that leads into some other course that we teach or some other theory or whatever may be the case. All right, so this is it. Let's then, if you don't have any more questions, let's give you a break, and then we'll pick up on Tuesday with the rest of the